Cool. So we'll get started with our feature presentation. We have Mark Engelberg with us today. Mark uses Clojure not to build games directly, but in order to help him develop games like Animalogic, and so he'll talk about that specifically, comparing that, doing that in Clojure with Java, as well as showing you some parts of Clojure that might be underutilized that you could actually benefit a lot from. Mark also teaches Clojure. For those of you who are fighting the good fight at your companies to get Clojure more widely adopted, perhaps you're laboring in a dark corner, using it for I don't know, a piece of data or scripting, and hoping that more people will adopt it. Mark actually does teach Clojure, and he can come in and give you guys a boot camp of any length to level people up and help them see the light. So, Mark Engelberg, thank you for joining us.
Thank you very much, Dave. So I am a puzzle and game designer, and that starts with this process of inventing a game, just kind of coming up with an idea in my head. But then most of the games I develop are puzzles. They're solitaire puzzles that come with a bunch of equipment and a book of puzzles that you flip through, and you set it up, the board, with that specific instantiation of the puzzle, and then you work through it and solve it. So I need to then write programs to help me generate these puzzles, to solve the puzzles, to test them, to analyze the difficulty. And that's a process I go through with each puzzle that I developed. So today I'm going to be talking about Animalogic, which was one of my very first games that I invented. I first came up with the idea back in, I guess it was probably about 2005, showed it to a publisher around 2006. It takes a while for things to actually get published once they accept it. So it came out in, I think it was 2008. It got nominated for the Spiel des Jahres in Germany. It won a Parents' Choice Gold Award here in the US in 2009. And when I first came up with the idea, I was thinking in terms of developing like a solitaire card game. And then it kind of mutated into this. And the very first thing I wanted to do was sit down and do some analysis, like how solvable would this be if I played it as a solitaire game and dealt it out randomly. Would this thing be generally solvable or not? What dimensions would make good dimensions for this board? I did the initial coding in Python, and then a couple years later, when I was approached to potentially do a sequel for this game, I started porting my code over to Clojure, because at that time I had shifted all my Python work to Clojure, and you'll see why as we go through the code and take a look at how nice it is in Clojure. You'll see why I switched. But I've been thinking about Animalogic again recently for two reasons. One is I just found out it's going to be re-released by a company based out of Israel. They're the same company that develops the famous Rummy Cube game you might have seen with like the mahjong tiles for the Rummy. And they're producing it under the name Logic Cross. So there's going to be a new edition with different colored animals, but the same basic idea. And the other thing that really got me thinking about this again is I happened to receive an email a couple months ago from a 14-year-old girl who was homeschooling and learning how to program, and she had played Animalogic and had kind of captured her imagination. And so she sat down and wrote a solver in Java for Animalogic, and she emailed it to me to show it to me. And I was really impressed because like several years ago, a student had once emailed me some Animalogic code that he had written, but it was an engine for basically playing the game. And whenever a student approaches me with something like that, I'm always like, wow, that's great. Here's another challenge for you to think about. So when this was a senior who had taken AP computer science in Java, and he sent this to me, and I wrote back and was like, this is great. Now, why don't you try making a solver for this so you can determine whether these puzzles that are randomly being generated are solvable or not. And that was beyond the scope of what he had learned in his AP classes. So I was really impressed with this 14-year-old girl, Samantha from New York. If anyone watching this video later wants to get contact info to offer her an internship or something, let me know. But I was really impressed with what she did, but it also got me thinking when I saw her code, and I'll show you some of her code, you'll see it just reminded me of how verbose Java is compared to Clojure. And so we'll do some comparisons between the approach in these two languages. But before we can do that, I first need to show you how the game works. So Animalogic, there's 4 animals. The animals are lion, hippo, camel, and giraffe, and they come in 4 colors, red, blue, yellow, and green. So each puzzle shows you a way to set these animals up on the board. And what you're looking at is there's 4 rows here. So I've written one of the puzzles I've copied here onto the board. Now there's this river on the left side of the board, and the idea is you're trying to get these animals to cross the river. Well, you have to take them from the left edge of their rows. And initially you can pick any of these 4 animals. But once you pick one of these animals, then the next animal you pick has to match either the color or the animal type of the previous one. And your goal is to keep doing that, pulling them off from the left edges of their respective rows, trying to get all of the animals off the board following that matching rule. So just to make sure everybody understands, let's just quickly run through this with this. Maybe we'll solve it, maybe we won't, but somebody shout out the first 4 choices are green lion, green camel, yellow hippo, blue giraffe.
Green camel.
Green camel. So the green camel goes away and is the first thing in our lineup. So now the next one has to either be green or a camel. So we could go with, it looks like the green lion is the only one of these 4 choices that could possibly work for the next one. So we're forced there. And now we're looking for either green or a lion. We have 2 choices now, blue lion or red lion. Neither of these match. The yellow hippo or the blue giraffe does not match. So red lion. Okay, next we need to get either a lion or a red animal. Looks like our only choice is going to be the blue lion. Okay, next, blue or lion. We can either go with the blue giraffe or the yellow lion.
Blue giraffe.
The wisdom of crowds. Okay, next we're looking for either blue or giraffe. Uh-oh. Dead end.
You killed us at last.
So we lost after 5 moves. So we'll stop there. You understand how the rules work, but there is a way to pick them in order to get all 16 of these on. You're always picking from one of the leftmost animal available in a row, and it has to match the color or animal type of the previous one removed.
Got it. I missed the first half.
Okay. Any questions about how the game works?
Is there always a solution, or sometimes not?
So all the puzzles in the book definitely have solutions. One of the first things I did when I first wrote that Python code to do the analysis, when I was really excited and, gee, does this idea hold water? The first thing I did is I randomly generated a bunch of boards and just ran the program to see what the probability is that they would be solvable. And I actually found it's about an 80% probability if you randomly deal them out that it will be solvable. So it's actually pretty good as a solitaire game. You can just kind of randomly set them up. And there's a pretty good odds you can get all the way through if you kind of see how to do it. Of course, the average difficulty of a randomly generated one is kind of a middling difficulty. So if you want to make them especially easy or especially hard, you have to use different techniques, which is one of the things I'll talk about.
How would you, how do you measure the difficulty?
I will be showing you exactly how I did that. But in general, the approach to generating these puzzles, a lot of people wonder, I mean, I do this with all my puzzles. People say, like, what is the strategy for generating puzzles? And I always say the first thing you need to do is you need a good solving engine. Because whatever you do, you're going to be solving things. The second thing you do is you need a way to assess the difficulty or the interest level of the puzzle in some way. Once you have those two ingredients, then generating puzzles is just a matter of just generating a bunch of stuff randomly, testing to see if it's solvable, measuring its interest or difficulty level, doing that thousands of times, shoving them in a database, and then, like, sure, there's some kind of normal curve. Most of them kind of fall in the middle, but you can pick some really hard ones, you can pick some really easy ones, you can pick whatever you want out of the database once you do that. So that's the general strategy for all these things. So let's go ahead and get into this. So this is how Samantha's code starts out in Java. She does what I think most Java programmers would do. We have some data we want to specify for our game. We have this concept of a piece that could have, an animal can have different color types, it can have different species types. She used this done sentinel to make it a little easier. It makes her code a little more elegant later when you've got, she used that for like the end of the row rather than kind of an empty list. It was just a choice she made. But you know, this is kind of how you'd set it up. You have here a constructor, getters and setters. You have a way to convert it into a string. You have the matching code is pretty straightforward. That's the heart of this. And then she has different ways of kind of building it from strings. And then I noticed the next main class she has here, she's essentially simulating a rep. This code is essentially building her own REPL. She's created like some prompt where she can type in boards using 2-character strings, and then it'll process the solutions and print them out. So it's a great start. I think this is the way a lot of programmers would start, sitting down in a language like Java. When I saw this, though, I was reminded of a great talk by Alex Miller. And this is one of the slides from his talk. I don't know if you can see this. He was comparing, we use Clojure data all the time, and he was comparing what you have to do in Java to get the kind of simple data that we use in Clojure. Just so I know, because I don't have a good sense for the demographics of who's here. Who here uses Clojure regularly? And who's here like kind of new to Clojure, just sort of checking it out? Okay, good. Okay, good mix. So this is, well, first let me show you what it compares to. The next slide on here is, this is what it would look like in Clojure. We have just some simple data that has a first name, a last name, a Twitter account, an email address, maybe a bio blurb, and a picture URL. So now let's go back and look at what you'd have to do to implement all this kind of stuff in Java. So the first thing he does, he's creating this speaker class. This is for like speakers at a conference. And you've got some fields for these, first name, last name, Twitter ID. Here you have a constructor that just takes arguments and shoves them in there. And of course, the proper thing to do in Java is to access all this stuff safely with getters and setters. Now, if you want to be able to compare two pieces of data in Java using like the content, comparing the contents of these things, as opposed to just comparing whether they're literally the same object stored at the same address in memory, then you have to override equality. And in Java, so this is an overriding equality to compare these two objects field by field. And in Java, anytime you override some equality, you're also supposed to override hash code manually. So here, this is overriding the hash code with some standard hash code material where you like take 31 and you hash the individual fields and multiply this prime number by it over and over again. And then you need, and we saw this in Samantha's code, like a toString function, some way to print these things out. Like this is the kind of stuff you would have to do to just use data in the most simple, straightforward way in Java. And you know, it takes all that boilerplate code. It's so much nicer to be able to just write this and to start using it and have equality work the way you want, and for it to be able to store this stuff in hash maps and hash sets, and everything just works because the hash code maps the equality semantics when you're comparing these things by their fields. Now, one of the things you're missing in this map representation is you're missing the actual type, right? This was class speaker. Well, we have a couple solutions to that enclosure. One way is you can just add a field called type if you want to. The other way is you can use what are called records. There's something called def record enclosure, and that gives it a proper Java type that you can use to do polymorphic dispatch based on type if that's what you want to do. So when I was reminded of this when I saw her code, because she's doing exactly what I think what you would do when you'd sit down in Java, but it's so much more complex. I haven't even shown you the solver yet. This is like the stuff she had to do to just get started. When I saw this, the first thing I did is I mailed it back and I said, not to intimidate her or anything, but I was like, by the way, I have a 9-line version of the solver. It was more just to kind of tempt her and like be curious, you know, what language are you using where that is possible? So what I've done here, so notice how I don't have to describe the data. And this is actually something I'll be coming back to, which is because I was able to write this code in a way without describing the data, this is totally agnostic about, like, it doesn't care that I have to pass in specifically red hippo or red lion. My earliest version of this, I used playing cards. And so I could easily specify playing cards and pass this into the solver. It doesn't even care what the dimensions of the board are that are passed in. Like this code's going to work not only on 4x4 code, but it could be 6x6. It doesn't even have to be a square board. It could be, you know, a 3 rows, 4 deep. It's completely agnostic about all that. It doesn't even have to be just 2 attributes. Like if I wanted to make another version of this puzzle where, you know, you have small yellow hippo and large yellow hippo, and you can pull something out of the lineup when it matches on any of these 3 attributes, this solver will do it all. So it's not just about concision. I mean, yeah, it's nice that you can do this in 9 lines or whatever, but what's really cool about it is that because I didn't need to sit down and specify rigidly all these classes of what my data was going to look like ahead of time, I ended up with code that's more general. So to explain, so first is the matches code. It's going to take, so let me show you how I'm representing things. So an animal is just going to be a vector of, it could be 2 keywords. Like this would be an animal. And that just evaluates to itself. There's also the ability, and I do this simply because it's easier to type. You can put a quote in something and it'll evaluate these variables as what are called symbols. And symbols behave almost like keywords. There's a subtle difference. The big difference is that when you evaluate something with keywords, the printed representation looks exactly the same as what you passed in. When you quote something that has returned symbols, if you pass this in a second time, it would think red and hippo are variables, and it would try to evaluate them if the reader sees this. So that's the difference. A lot of other Scheme and Lisp and some of those things just had symbols, and this was always like a little gotcha in those languages, is that symbols don't quite, they're printed representation. You can't pass it back in again and get the exact same thing. So keywords kind of solve that. But my program doesn't care as long as it's a vector of 2 elements. Or it doesn't, like I said, it doesn't even have to be 2 elements. It's just a vector of attributes. Let's take a look at what a puzzle looks like. So each row is just a sequence of these animals: red hippo, yellow giraffe, blue giraffe, green hippo. And you can see I specified it. The reason I used symbols instead of keywords was simply because I could put the quote at the beginning and it saved me a lot of typing. But either way works. But each row is just a sequence of 4 animals here. And my overall game board is a vector of the 4 rows. Does that representation make sense? So with that in mind, you can see, so matches is going to take 2 animals. And what we're doing is we're making sure this is sort of a higher order function that sort of goes through each of the attributes and makes sure that at least one of the attributes matches. That's what that line says. And this is a way of writing it that generalizes across whether you want to have 2 attributes, 3, 4, whatever. That code will work. Now to explain this solve state code, I thought it would be easier to break it out in, yes, the 9-line version's cute, but for clarity, I'll show you kind of what each concept in there does as a separate function. So the first thing we want to do is we want to evaluate. So in addition to having a board, if we wanted to talk about what is our state at any given point in time while solving this, there's the board, and then there's the line of animals. So when I say my input is going to be a state, I'm looking at an ordered pair of the board and the line of animals. So what are the possible moves if you have a state of a given board and a given line of animals? Well, what we're going to do is we're going to go through each of the rows, and if the line was empty, like if we don't have any animals out yet, then we're good. That row is a valid candidate. So what we're looking for here, just to be clear, so I want to get back the row numbers, the row indexes of the rows that are valid moves. So this is with this test puzzle. If you got no animals in the line, this is what's valid. So either the line is empty, or now this seek of board I, seek is due to what Clojure does what's called nil punting. And so seek of board I is a way of saying not empty, essentially. So we need to make sure that the row is not empty, and that the first thing in the row matches the last thing of the line of animals. And peak of the line gives you the last thing in the line because the line of animals I'm representing is a vector, and peak on a vector gives you the last element. So we're pretty much saying, and for in Clojure, it's not like a traditional for loop. This is what's called a sequence comprehension in a lot of languages. So what this is actually doing is generating the sequence of all i's that fit this category, that fit this description. Once we have some candidates, we want to be able to make a move. And we get back the new board state. You can see how an animal's missing from row 1. This is 0-based indexing. So there's an animal taken off the front of here, and it's been moved to the line of animals down here. So let's see how this works. What I'm doing, so I'm using here a technique in Clojure where we destructure the inputs. So I'm saying right here I'm expecting a vector of a board and a line, and that automatically destructures it when it's passed in. And then I'm building the vector of the new board and the new line to pass out. So the new board is I'm going to take the ith row and I'm going to update it by calling rest on the sequence. That chops off the first thing. And then I conj the first thing from that row onto the line, and that sticks it on the end of the vector of the line of animals. So with these two things together, we can pretty easily define this concept of from a given state, what is the next, what are all the reachable states I can get to? Well, from a state, I'm going to generate all the possible moves. And for each of those moves, I'm going to make the move. And that's going to now generate the sequence of all the reachable states. So let's try that down here. So it's generated, you're seeing the last two of the four states that you can get to from the first position. The other two scrolled up there. Now we need a way of finding out when we've won. And we've won when every row of the board is empty. Then we can actually make a function that from a given state, meaning a board and line combination, we are going to generate all the solutions you can reach from that state. And this is a recursive procedure. So the base case is if we've won, then the set of all solutions reachable from this state is just the line of animals that you've reached at this point when the board is now empty. Otherwise, we're going to call reachable states on the state to get all the next states you can get to. And we're going to recursively call solve state on that. And each of those is generating a list of these, all the solutions you can get to. So you want to combine them using mapcat. So mapcat is a combination of map with concat. So we're mapping solve state on all those states, getting back all these lists of solutions, and then concatenating all those lists together. That's what mapcat does. And then we can have this nice little helper function, so we don't have to keep typing the board and the empty list all the time. We can just make our lives a little easier by making a function that you just type in the board and it kicks the whole process off with the empty animal line. And that's pretty much what is going on. This is just combining all those pieces into one function. But it's exactly the same as, it's all those functions just combined into one. Any questions about the solving code? Yes?
What's the reason you care about the whole line as opposed to just like the most recent?
You need the whole line to get the solution at the end.
Okay.
You're right that the only thing that matters from determining the next moves is the topmost animal. And later when I'll show you another version of the solver that I use to measure the difficulty. That version of the solver, I consider a state as being just the board with the most recent animal, because that's all that matters with respect to next moves. So that's a good observation, but you need to capture all the information about the line to be able to report the solution when you get to the end of the process. Any other questions about the solving code? Okay. Now I want to contrast something about this with Samantha's version. So this was her first depth-first search version. Her very first version she sent me had a somewhat different search strategy, and I kind of pointed out to her that it's perfectly reasonable to do a depth-first search on this because it can only go 4 deep. And when you have a depth-first search, you can take advantage of recursion to not have to manage the stack of possibilities to try manually. So I encouraged her to try a depth-first search version that took advantage of recursion, and this was the first thing she came up with. There's one key thing here that's very different about my version, and I'll give you a second to think about it, but I don't want to take too long. Does anyone see the key difference that I'm thinking of? And
Mutability.
yes, and what is the consequence of the fact? So that she's used a mutable representation of the board so that she can, she's imagining there's a physical board there and you're removing an animal and you're putting it in the line, right? That's the process we're used to from Java. It's exactly what I think someone, almost any Java programmer would do. So it's not a critique of her, it's just this is the way you do things, right? But notice there's one key thing that you have to remember when you're doing mutable code. So she removes the animal and puts it in the line of animals removed, and then she calls recursion, and then she has to remember to put the animal back. Actually, one of the first versions she sent me of this forgot to put the animal back, and I pointed out that's not going to work the way you think it does. And so she fixed it and put this in, but that's a really easy thing to miss. And on top of that, it doesn't necessarily generalize well to other strategies. Like, if you're doing a breadth-first search and you're manually managing this queue, it's not so obvious how you backtrack from one state to the next one, or that it might not have that clear sequence of operations that you can just immediately undo and let the recursive functional call stack kind of handle all that stuff for you. And some puzzles, it's just not always obvious exactly how to do the reversal. It's not always so easy to describe the reversal, but it definitely gets thrown off if you need to do anything different than a depth-first search. So I said, okay, this works, this is good, but I want you to think in terms of immutability. One of the things I have found very freeing, one of the reasons I moved to Clojure is because I found that especially the kind of work I do with puzzle solving searches, things like that, it's hugely freeing to not have to worry about doing something destructive and somehow undoing it. Just to be able to keep exploring these states and looking at them as immutable entities, generating a new set of immutable states that I can explore, put on a queue, do whatever, it's just hugely freeing. So I said, go try this. And when I said that, I was thinking like she would find this to be this incredibly liberating experience. And I think she did get something out of it, but part of what she got out of it was this is really hard to do in Java. Let's see if I can find some good examples in here. So she ended up having to, the heart of it is this perform move code. She had to kind of manually do a lot of stuff to make a clean copy of the board when you're doing the move, and a clean copy of the line of animals removed, and build it up properly. So she had to think about like how to do that with copies. And it comes up in other places too. So there's just a whole lot of code in here about dealing with making sure you've got clean copies of things. And then in one of her first versions, she was also making copies of the animal objects themselves. And I pointed out that those you never actually mutate. So those you don't need to worry about copying. And it's like, okay, now you got to worry about which things you need to copy and which things you don't. Like it was, I think she saw that now once you have the copies, you can do the recursion here and not have to worry about the undoing it. And that is freeing in some way, but she had to do a lot of work to get there. So this is one of the reasons, like this was one of the things, I mean, when I did this in Python, I dealt with the same issues, all the mutability stuff. And one of the reasons I quickly adopted Clojure when it came out was I saw, here's a language that has all the things I'm used to from Python. It's got the hash maps, it's got the vectors. It's not just like Scheme where, all you can do is lists or whatever. It's like you got all these things that are the things I'm used to working with. And they're all come in these immutable flavors. And I can do this kind of stuff without a lot of deep thought. And it lets me come up with the clean code like this. Now, the next thing after having a solver is to assess the difficulty in some way. We talked about, and you were very curious about how that works. And this is something that is a lot of trial and error for me. It's like I come up with some ideas of an interesting way to measure it, and then like I'll play the game and compare my ratings against what the algorithm's telling me. And I'm sort of using my instinct as a game player and as a puzzle solver to try things out, try candidates out, and see what I like. But one of the things I knew I wanted right away is I knew I wanted to understand, whatever my measure is, I want to be able to understand this whole game space of all the possible states I can get into. So what we're looking at right here is you start from, and this was back when I was playing around with playing cards, so these are in columns rather than rows, but it's the same idea. So from, this is your original board state, and these are the 4 moves, the 4 different states you can get to. And we're following these different paths down. And at the end of all this, you either get to dead ends, which I've colored red, or in this particular puzzle, there's the one winning state. There's only one possible card you can have on top at the end. This is where for understanding this graph, this is where I made the distinction of all you care about is the top card. Because even if or I call it the top card because I programmed this when I was dealing with cards, the last animal is all you care about. Because regardless of how you got to that position, whatever sequence of moves, whatever the last animal is going to determine what comes next. So you want to, if you didn't do that, then you'd end up with just a crazy number of states. So this way you can potentially arrive at the same state in a few different ways. But there's this one state you can get to that wins. So one of the things I realized upon thinking about it is, like one of the first things I tried was, well, compare the number of dead ends against the number of ways to win. But that turned out not to tell the whole story. Because what seems to matter more is like, how far can you go down these dead ends, right? It's these, so what I did is I kind of colored all the states green that you have a way to win. All these things that are colored white, if you're in that state, you're already dead, you just don't know it yet. So what I found after trying a whole bunch of different measures, what I found was count up the number of states, get rid of the actual terminal winning and losing dead ends, the actual final states, but comparing the whole interior, looking at the ratio of states where you can still win to the overall number of interior states. Like that ratio I found to be a useful measure. Or actually, I guess you divide it the other way to get a score that grows larger means more difficulty. Does that make sense? So that's what I arrived at after playing around with that. Now, to represent this, I needed to make some kind of graph data structure. I needed to start at the beginning and unfold this tree of possibilities. But then I'm going to need to take the winning state and move backwards through this graph of possibilities, coloring in all the states that led there as winnable. So I can't just represent this as a tree or a directed acyclic graph. I'm going to actually have to represent this as a graph so that I can both go down and then go back up again at the end. And for some of you who haven't done intricate data structure work in Clojure, or any immutable language, it might not be obvious. How do you do things with cross-references in an immutable language? If we were in a mutable language, it would be pretty obvious what you do. You have a pointer, and you set this pointer to this thing, and then you move down to this thing, and you set this pointer back. But when you're in an immutable language, it's not quite so clear how you get these mutual references. So what I want is I want a node in my graph to basically have 3 pieces of information. It's got some kind of name, and my name, in Clojure, my name can literally just be the state, the board and the line, or the board and the top card, can be the name. And that's because it's immutable. And so we can just use it as a piece of data and store it in as keys and hash maps and do things with it. One of the things back in my Python version, I did something kind of similar to this approach, but I had to have a lot of code to convert every state into some kind of string representation, because strings are like one of the only really immutable. You're only allowed in Python to use immutable objects as keys, and your choices for immutable things are basically numbers or strings or tuples, but not arbitrarily complex data structures. So I had to do a lot of conversion back and forth. As I would move through this graph, I'd like get to a new state, convert it to a string, use it as a label to enter something into the graph. It ends up being so much cleaner in Clojure, and I'll show you the code in just a moment, when you can just use the data structure as your name. So this is going to be my board state. And now I'm going to have a list of children, all the descendants in this tree. And then I also want each node to have the list of parents. Now, the key to making this work in an immutable language is when we put the list of children, we just put the list of names. We don't actually point at the whole data structure. So what we're doing, our graph now is going to be a map. And it's going to be a map from these names or board states to this whole data structure of name, children, parents. So from any name, we can look up the corresponding node in the graph. And this now becomes something, like because it's all in this map, it becomes really easy to update. Like if I want to update some fact and say that a given board has this new child, what I'm doing is I'm just updating, I'm adding a name to this. And then I can later add more information about what that name goes to. So it makes these pieces of information more, there's this level of indirection that is almost serving as a pointer. Instead of directly going from one piece of data to another, we're going from data to a name that we can use to look up the data. Yes?
How do you generate names for the board states?
I'm just using the board states as my names. I'll show you that in a second in the code, but I'm literally just using the board states as the names. With one twist to handle the concept that I want states to be treated the same as long as the last animal is the same. So I'll show you how I did that twist. I used a little trick that comes up in other contexts in Clojure. Now, recently I developed, well, I say recently, it's probably been a couple years. I developed a graph library for Clojure called Uber Graph. And that's because I do a lot of this kind of work, and I wanted sort of a general purpose graph library. There's another popular one in Clojure called Loom. And Uber Graph is kind of an extension of Loom. Loom is good for certain kinds of simple graphs. But if you have different kinds of arrows, and sometimes they might go along the same path or whatever, like Loom doesn't handle those sorts of scenarios. So Uber Graph just handles more situations. If I were to do this again, I'd probably use Uber Graph because I wrote the library, I would use it. And it's got a lot of searching utilities built into it that are very efficient. But this code I wrote before I'd done Uber Graph, so I'll show it to you and you'll get a chance to see what kind of an ad hoc graph representation looks like in Clojure. And I think it actually shows how it's not that hard to write these things yourself. And you'll see some of the traversal code that I wrote manually here because I didn't have ubergraph written. Can you see that? Yeah. OK. So I'm using this to establish the difficulty of these games. And this is all as part of, now I'm going to be generating a big database of these things. So because I'm going to be using this in generation, I need to know what size board I'm actually generating for. So I chose to make that as a global rather than an input to a function, because I knew at this point I was pretty much going to be focused on 4x4. I just wanted to retain the right to expand this stuff later. So my game state, I didn't just use a record and I didn't just use a plain data because there was a little trick I wanted to use here. The trick is metadata. In Clojure, any map, any piece of data can have metadata associated with it. And what's really interesting is that in Clojure, the equality semantics between two objects ignores the metadata for purposes of equality. So I knew I wanted to have solution information carried around in these states so that when I look at the states at the bottom, I can read off the solution. But I didn't want that to be used for equality purposes. What's the solution in Clojure? Shove it in the metadata. So I wanted to make it really easy for myself to construct data that would store the solution in the metadata. And I wanted a uniform way to get that. Once you've done a trick like that, though, you can't just use keywords to get out the data from everything, because now solution is going to look a little different than the other things. So I went ahead and kind of made a constructor for myself and made selectors to get these pieces of information out. The solution pulls it out from the metadata. I didn't have to write this stuff, but it makes the code look more uniform later, even though I'm storing one piece of data in the metadata. So a lot of this terminology comes from back when I was playing around with this with a deck of cards. So instead of a board, I call it a tableau. When I talk about a deck, I'm talking about like the deck before you've dealt it out into the rows. So just your line of all the possible cards at the beginning is the deck. You'll see this code, the reachable states code, is almost identical to the other one. It's just the top card is now its own individual entity, so I can just compare directly against the top card. But it's basically the same code as before. Winning state, basically the same as before. Now we get to the graph code. So this is one more thing about immutable graphs. We were talking, one of the things I knew I wanted to do is I wanted to go through and mark certain nodes as winners and certain nodes as losers and some of them as winnable nodes. How do you mark something when it's immutable? Right? This comes up in a lot of graph algorithms. A lot of graph algorithms involve traversing a graph and marking some field as true or false. Well, because each of these node labels can be used as keys in a hash set or a hash map, a really easy way to mark things in an immutable graph is to build up a immutable set of all the things that satisfy a certain criteria. So ultimately, my goal is to build a graph that's going to have the root of the graph, this mapping of all the nodes, names to the overall bit of data about a node, which is just the state, the children, and the parents. And then I also want to store these three sets. Now, I'm not going to be able to build this all right away. I'm going to do it in multiple passes, but that's perfectly fine. There's no reason you can't do it that way. So these are some helper functions. I'll get back to this in a second if it makes sense to do that. Let me go down here to the build the graph. who's here is familiar with transients enclosure? So transients is a little trick where if you're building up a large immutable thing, you can mark it as transient at the beginning, basically saying, I don't care about these intervening stages, I just care about the end result. So like, make it mutable for now. So you create this thing that's kind of, it's mutable, but it responds to a similar immutable interface as the other objects in Clojure. So you can use it as a drop-in replacement in your code. And then at the end of it, after you've added all these things to this mutable set, you say persistent, and it turns it back into an immutable thing at the end. And it just makes it, it's a speed trick to build up things. So here I start off with these transient maps and empty maps and empty sets that I'm going to be adding things to, and I'll mark it as persistent at the end. Here I'm kind of manually managing a queue. The queue starts off with just the root state in it, and as I explore new states, they're going to be added to the queue, and I keep like going from each state, expanding the states, recording the children. Here I'm using a trick. One of the things that I'm a huge fan of is the ability to put let clauses in the middle of a cond. So I wrote a little library, because I do this all the time. One of the issues with Clojure is every time you do let or cond, you're introducing a new level of indentation. When you go back and forth between, you take a couple cases, and then you want to give a name to something, and then take a couple more cases, and then give a name to something, you end up with this just crazy deep indented code. So this is a little thing I wrote to make it easier to drop in let in the middle of a cond. And I call that library bettercond. You can find it on GitHub. One of the things I do as a little trick I have in the bettercond library, you can say defn C, and the C basically wraps the body of this in an implicit cond. So there's like this imaginary cond around the whole thing, so you could start right away with the colon let. And you can pretty much, and this cond also allows a final clause that doesn't have an else. So if you do use def and C and just write normal code, it works also, because it's a cond that basically just jumps right to the thing you just wrote. And this is something, it's this kind of a in-depth thing in Clojure, this loop recur strategy for iterating over things. We get so used to using higher order functions in Clojure, most of the time you don't need to drop down to this level. But this is, if you need that level of control of essentially simulating a while loop, sitting in a loop doing something, this is the technique for doing that in Clojure. So anyway, so we're generating all the children from the reachable states, we're recording all that, and then once, let's see, where is this? This is kind of one of the base cases you get back to. Once your queue is empty, you now have these things built up, the winners, the losers, and the map of all the nodes. But I was only able to record the downward direction at that point. So here, so I'm calling persistent on all these things. Add reverse edges just takes all the children edges, flips them all around, and builds the corresponding parent edges. And then add winnable goes through bottom up, following the parent chains from the winning nodes, and adds in a new set of all the winnable nodes. And you end up with this data structure that I was describing, where you have the map from the board states to that, plus you have the winnables, set of all the winnable states, set of all the winner states, and the loser states. The rest is just details, but this gives you an idea. I mean, so it might look long because of the big font, but the main traversal of this graph and building up the graph is not a whole lot of lines of code. And then I've got a couple helper functions to do all the reversing of all the edges. They're fairly short. Like this is a helper function just to do the reversing of all the edges and add that in a clean way. But each of these little pieces is fairly small chunk of code, half a dozen lines or so. Any questions about the graph representation and how I used it to measure difficulty? So now we get to some of the different difficulty measures that I experimented with, and the one I did at the end was this difficulty 4. And I found this to be a pretty good measure. Any questions about this?
Is interestingness and difficulty the same or different?
To me, interesting, like I don't have a literal number for interestingness, but what I do is I try to capture several different statistics. How many nodes are in this state? The difficulty is one of the measures. How many different ways to win are there? Different ways to lose? Like all those statistics are kind of interesting. And so what I do when I try to actually build out a set of 40, like I generate a huge database of these things. And if we have time, I can spend about 10 more minutes maybe showing you some of the database code, if you're kind of curious to see that piece of it. But I stick a lot of these puzzles in a database, and then I can search for different attributes to make sure I get a mix of puzzles in these sequence of 40. Like in the early puzzles, one of the things I found is that there's sort of like 2 categories of easy puzzles. There's puzzles that are easy because at each point in time, you pretty much have one choice, or maybe 2 choices where one of them is obviously a dead end right away. So like if you were going to draw that graph, it's kind of like almost a straight line with these couple like forks that go nowhere. That's one kind of easy puzzle. Another kind of easy puzzle has this big sprawling state space, but almost everything leads you to a win. So like you feel like you have a ton of choices as you're playing it, but there's almost no way to go wrong. So what I try to do, once I identify that there's like these 2 different ways to be easy, I can search the database on these different criteria to try to get a mix in the easy puzzles alternating between these 2 different types of easy. So yeah, I kind of use the terms interchangeably, but to me difficulty is like one piece of understanding what makes things interesting. Another possible direction I could have gone with difficulty, and something I've done in other puzzle games I've developed that weren't as amenable to some kind of direct mathematical measure like this, is I would create a simulated naive player that plays through this thing. Maybe like in this game, I would say it plays through randomly unless like it's obvious that this move is going to go to a dead end right away, in which case I'll ignore those things. So I figure like even a rookie player will be able to spot those. So I'll make like a model of a very naive player that is basically making random moves except for a couple things they can see. And then I'll just run that like 100 times and sort of see like a player playing with that strategy, what is the percentage of times they win? And that would be another perfectly reasonable way to rate the difficulty, is using a simulated player. And I do that in a lot of my puzzle games. On this one, I happened to find a measure of the graph space that I thought worked pretty well. Let's take a look at the generator code. Okay. I actually have versions of this. If anyone's curious to look later, I have versions using H2, which is a SQL database, and a couple different, there's a couple different Mongo interfaces. The one I use the most is Congo Mongo, is the Clojure library. There's a couple out there. There's like Monger and Keras and this one, but this is the one I've used the most. Now what I'm going to be doing is I'm going to be making a function that generates a puzzle and inserts it into the database with a lot of these measures. So let me show it to you in practice. So it created the puzzle, and one of the things I like about Mongo is it has a relatively low impedance mismatch with Clojure as opposed to the relational databases. Basically, it feels like you're putting in a map and you get a map back. And that works really nice from Clojure. The catch is you can't just put in arbitrarily complex data. It still is expecting, numbers or strings for the most part. So I do have a way of converting. This is like a string representation of the puzzle. So 0, like I index the attributes as 0 through 3 for each attribute. And this is a bunch of pairs just concatenated together. So this is my string representation of the puzzle. Another little gotcha with Mongo, I don't worry about it so much these days because now I do store most of the data in the cloud, and I don't worry so much about how much storage it's taking up. But back when I did this, I was running it on a fairly low-grade laptop. And one of the catches with Mongo is each row, it's storing that key value pair, like it's storing the key over and over again. And what is nice about that is there's no schema that you have to worry about. So like one of the things that would frequently happen is I'd be generating some puzzles, and then one day I wake up and I go, oh, I just thought of another measure I would like to add into my data. I don't necessarily want to go back and add it for everything I've already done, but I can start from this point forward adding things to the database with this new attribute in there. And it's so easy to just start adding new attributes and throwing it in the database. You don't have to rework the schema. So that's one of the things I like about Mongo. But because I was concerned about the repetition of the key and how much storage that would take up, I made one-letter keywords for each of the different attributes. I wouldn't do that these days, but that's what I did back when I wrote this. So it's taking all these entries, storing it in the database, and then I have some functions that let me fetch the puzzle out. I can either look it up by string or look it up by vector. When I say vector, I mean the actual puzzle description of the board, to see if something's already in the database. So I use that like as I'm generating them to make sure I'm not generating one that's already in there or one that's equivalent to one in there. So there are things like if you just swap two rows, it's still basically the same puzzle. Or if you swap around the animal types, like change all the hippos to giraffes and all the giraffes to hippos, it's still the same puzzle. So I make sure that I'm putting things in the database that aren't equivalent to something I've already put in there. And I also have some special handling. I noticed that one strategy people sometimes employ when solving these things is they try to work backwards. Well, working backwards on these puzzles is just like working forwards on the puzzle where all the rows are swapped. So I wanted to make sure I didn't have two puzzles in there that were just left to right swaps of one another. So there's some code to kind of handle that. But basically what I'm doing is I have this generate puzzle thing that generates a puzzle. Canonical form basically comes up with one name for the puzzle out of all the different permutations or ways you could represent it, so that I have an easy way to check if it's in the database. So I check if it's in there. If it is, I just repeat this process. I build the graph. And the way I wrote the build graph function is it returns nil if there's no solution. So if the graph exists at this point, now I know I have a solvable puzzle, and I go ahead and insert it. And my insert puzzle code is analyzing the graph to come up with all these measures. Does that make sense? One of the things I did here is I take I have the difficulty, but then I have this field A, which is a weighted average of if you were like trying to solve it forwards versus backwards, to kind of come up with a difficulty that considers that people might approach it from those two different directions. Once I have that code, one of the great things about Clojure is how easy it is to take some of these pure functional pieces of code and spin it up on multiple threads. It's just a totally trivial job here. So what I did is up at the top of my code, I create an atom called halt ? And it starts off as false. And the whole purpose of this is that I'm going to be spinning up a bunch of threads. And every time through the loop, those threads are going to check to see if that's been set to true. And if it's true, then they all quit. It just gives me a way to, at the REPL, to shut all the threads down cleanly and easily. I have this little helper function called onThread, but it just does this simple stuff that is just Java code, which takes the function, creates a thread out of it, and then calls the start method on it. And then I have this little helper function called halt, which sets that atom to true. With all that in place, this generate puzzles code basically is start creating puzzles over and over and over again. At the very beginning, when I first call it up, make sure halt is set to false, like if I'm going to be doing repeated runs of this or something. And then it enters this loop, and it's checking always to see if I've set that field to true. And it's also checking to make sure like I haven't hit some ridiculous number of puzzles yet. And it's going to keep generating puzzles and just sits there in a loop doing it. And so then what I can do down here is I can do onThread generate puzzles. And it started up a thread. I'll start up a second one, a third one, a fourth one. How much of my processor am I using? So that sounds about right. I've got like 4 processors on here. Although it's one of those hyper-threaded things that in theory can do 8, but you know, whatever. So I was able to easily spin these up. When I want to shut it down, I call halt. Each thread is going to kind of finish what it's doing and then exit out. And now I can see how many puzzles I have. I just generated 10,662 puzzles in those few seconds by utilizing all 4 of my threads. So this is a technique that I use very commonly to generate puzzles across multiple threads. There have been times where I've needed to do more sophisticated things, where having threads be a little more intelligent about pulling things off of a work queue or something like that. But you know, because it's so easy to write this code that's nice and cleanly separated, it's easy to do this kind of thing especially. So I've shown you Mongo now, and I've shown you how I do multi-threaded. So I think it's about time to wrap up. It's been about an hour. Just to summarize, so some of the key reasons why I kind of switched over from Python to Clojure was being able to work with immutable data was really huge. To not have to worry about reversing states as I'm searching, but to be able to think of each thing as an immutable entity just makes all this stuff a lot cleaner. The second thing was being able to use these immutable data structures as keys in hash maps and hash sets allowed me to radically simplify my data structure code. Whereas in Python, I had to constantly be worrying about converting things back and forth to something immutable like a string all over the place, and it polluted my whole code base. And then third, you just get some of these, once everything's clean and immutable, you get some of these nice benefits of really concise code. And that comes not just from the immutability, but also the ability to work with lightweight data structures, to not have to define really complicated specialized classes for everything. By not having to specify that, I ended up with not only more concise code, but more general code that works on more things. And Yeah, I mean, I'm trying to think if there's anything else. I think those are the main points. Hope you all got a taste of why I like coding this kind of stuff in Clojure and what I do.